Hi everyone, my name is Madison Kramer. I'm going to be talking through Lab 3, which is our circuits lab. So to get started, the main objective was to kind of predict the behavior of different types of circuits. We threw some resistors, capacitors in there, but basically it's relating to these ideas and concepts of energy conservation and current conservation. Two main findings was that the total change in potential difference across a circuit was 0 and that voltage decays exponentially. Some key principles I want to go over. The first one's going to be Ohm's law, voltage equals current times resistance. It's really important that you can kind of relate the different principles within Ohm's law in terms of proportionality. Then capacitance, charge divided by voltage. The node rule is that current inflow is equal to current outflow, and the loop rule is that the total potential difference of a circuit is 0, which relates back to this idea of energy conservation. The first part of the experimental procedure is basically creating different types of circuits using batteries and resistors. The first one we created is an open circuit, and the second one we create was a circuit with ammeters in parallel. The second part of the procedure is basically creating, it's charging and discharging a circuit using capacitors, and then we created a time-dependent RC circuit. So some initial conditions and observations. One assumption we had to make is that resistance is manipulated in this computational model. Basically, the voltmeter has limitless resistance. One observation we wanted to note is that within this model, an ammeter doesn't have a negative sign when current's reversed. And the system is a circuit, and the surroundings is the area surrounding the circuit. So circuit 1, you got just 2 resistors, 2 batteries. The predicted current matched the computed current. However, again, it's important to note that we didn't see that sign reversal within the ammeter when the current was reversed. Moving on, we created an open circuit using a voltammeter. The reading at the battery was 3. There was 2 1.5 volt batteries, and the reading at the resistor was 0. It's important to note that the voltmeter has to have infinite resistance in order to accurately measure potential differences. Moving on to this idea of potential differences, we calculated them all throughout the circuit. You can see them modeled on this graph versus actually modeled within the computational circuit. So the main takeaway from this is that if you add up all the different potential differences, the total change is 0. This is the idea of the loop rule, which is conservation of energy. So you start and you end at 0. Next circuit we made was the ammeters in parallel. We calculated resistance using Ohm's law. So you can see this resistance calculated at various areas. It's important to note that there was no resistance in the wires or ammeters. So circuit 2, this is the second part of our procedure. We built that RC circuit. Charging was when we had the batteries connected, and discharging was the batteries were disconnected, and basically setting off the capacitors at different times. So it's important to note that with the charging where the battery was connected, when it was fully charged, no current was flowing. But versus and this was the same for the discharging, with the battery disconnected, fully charged, no current flowing. Alright, so that time-dependent voltage, this goes back to that idea of the RC circuit creation. And this, again, if you look at this graph we modeled, we have time versus the initial voltage as the quotient of the original voltage, or I mean different types of voltages we recorded. So voltage decays exponentially. And basically, we used this graph to model this time dependence, and when we took the slope of this graph, we were able to calculate the RC circuit dependence on time, which we found to be 7, and from the problem, we found this to be 6. So there was some sources of error there, which I'm going to break down. So breaking down the sources of error, there could have been an incorrect circuit setup, which I have demonstrated in this photo. That can come from misplaced batteries, misplaced ammeters, reverse flow of current. And then some conclusions I wanted to make is that real circuits must adhere to the effects of resistance. Strength of a direct current is proportional to potential difference, but inversely proportional to resistance, this idea of Ohm's law, and that voltage decays exponentially, as seen here in this decay curve kind of thing. So some reflection questions. If we did this in real life, we'd be at a disadvantage because ammeters have resistance in real life, which is like we would have less accurate values than we have in this perfect model. And then if we used a real battery to charge a real capacitor with no resistor, basically our ideal model would have this capacitor charged instantaneously, but this is not true in real life because we don't have negligible resistance. Thank you.